Our speaker for today is Dr. Jiayin Yuan. Dr. Yuan studied chemistry at Shanghai Jiaotong University in 1998 to 2002. He moved to Germany and completed his master's degree in 2004 and PhD degree in 2009. Next, he joined the Max Planck Institute of Colloids and Interfaces, Germany, and led a research group before he was appointed as associate professor at Clarkson University, United States, in 2017. In 2080, he landed in Stockholm University as a Wallenberg Academic Fellow, and since 2090, he has been a full professor in materials chemistry with research experience in functional polymers and carbon materials, covering basic research and applications in sustainable development. Since 2021, he has served as the director of the Stockholm Material Hub. He received the Starting Grant in 2014 and Consolidator Grant in 2022. We welcome you, Professor Yuan, and the stage is all yours now.
Thank you very much, Neha. Great introduction. So I think that you have introduced all the details. So thank you very much. And now let me share my screen. It's a great pleasure to be introduced into this online event. I must say that first, a good evening, and also to some of you say good afternoon to this event. My name is Jiayin Yuan. I'm professor in materials chemistry at Stockholm University. So today, I would like to use this opportunity to introduce our research line along the nanostructured polyionic liquids as functional polymers for energy and environment applications. This has been a research line for almost a decade, and you will, let's say, see the whole development of this research in my group. And something first about my group before I start the real scientific narrative. We focus on functional polymer and carbon materials. I was educated as a polymer scientist in my PhD time. And ever since, I have been working with polymer chemistry and polymer materials all the time. And two types of polymers are my interest. I work very intensively with so-called polyionic liquids and also charged biopolymers. Later, I also use polymers to template shaped porous carbons. Then I move to the carbon field as well. And not only the fundamental research of synthetic methods, properties, and function analysis, we also try to process polymers, carbons, individually or jointly into functional materials to satisfy a specific application. Here, very specifically, we try to develop innovative materials to address challenges for a sustainable society. Two types of functional materials fall into our interest. They are either colloidal systems or the porous systems. And that is also part of today's lecture as well. Here is the outline of my presentation today. So what I want to share with you. First off, we talk about polyionic liquids. So what this type of polymer materials is. Then we talk about nanostructured pills, why we are interested. Then we take two types of nanostructured pills, either colloidal ones or the porous ones, to demonstrate the research development in the group. At the end, I will summarize and also acknowledge the hard work group members. Now we've come to the scientific part about polyionic liquids. And polyionic liquids are defined as polymerization product of ionic liquids as monomers. So ionic liquids have been intensively studied in the past 20 years. And when an ionic liquid is equipped with a polymerizable unit, for example, a vinyl group here. I took the vinyl imidazolium bromide as a case study here. You could handle this monomer now by polymerization. And this simple polymerization produces actually a macromolecule where you have the ionic liquid species covalently connected to the polymeric backbone. Right. So this is a type of polymers. We call them polyionic liquids. And the field has different names for this type of polymers, but we use peers as a common term to name them. Sometimes you will see people use the called polymeric ionic liquids, polymerized ionic liquids. So they refer to the same type of materials, that is, the peers. Here I also list the 4 review articles and of the pioneers in the field. And they have been cited almost 1,000 or above 1,000, let's say, times in literature, so highly cited papers already. When you polymerize ionic liquids into peers, the merits you obtain from the polymer is the improved processability in terms of the, let's say, polymeric nature. And also you improve the mechanical stability and the shape durability simply because the high Tg of the polymers in comparison to conventional ionic liquids. And also you introduce a special control over the ionic liquid units in the polymer matrix in terms of polymer self-assembly and so on. So there are quite some merits in between. The Peirce concept is not something completely new. It is a natural extension of the polyelectrolyte research. So polyelectrolytes are polymers in solution that are ionized or ionizable. And this type of polymer have been studied for quite a long time, 70 or 80 or more than 80 years. So most of the people believe that polyelectrolytes have been fully understood, and they serve purely as a tool to support the other research fields. And when we study the peers, we find that peers naturally expand the property window and application scope of conventional polyelectrolytes. And this topic itself is still evolving, and you will see further development of the peer concept. In terms of the relationship between peers and ionic liquids and monomers, so here there's a single scheme where the overlap of the monomers and ionic liquids define a group of monomer that are also in the same time ionic liquids, and you can polymerize them directly into the peers. So this is a slide to position peers in the scientific research field. My group is very much interested in polyionic liquids, as I said, for quite a long time. And we are fascinated by polyionic liquids in the following points. First, the structure diversity. If you consider the combination of the polymeric backbone, the cation, and the anion, as well as the aqueous substituent, you could naturally end up with a number around 1 million, right? So the structure diversity is really, really huge. The next is actually the wide range of glass transition temperatures. Polyelectrolytes, usually they have very high glass transition temperature. Sometimes the glass transition is so high that they do not show any Tg before the somal decomposition. Right. If you come to peers, you will find that glass transition temperature can be unbelievably low, here minus 50 degrees C. That means some peers with rather low Tg, they can be in a fluidic state, even at room temperature. This is very unusual for polyelectrolytes. Next, peers have adaptive solubilities in organic solvents, particularly those of low polarities, for example, THF or acetone. These are the solvents usually used as a non-solvent for polyelectrolytes. But due to the concept of ionic liquids, the peers can naturally, let's say, adopt solubility in those low polarity solvent. This opens a new, I would say, environment to process peers in the environment usually polyelectrolytes are not suitable to. Here, one example is a membrane fabrication process, as I will introduce today as well. Then the heteroatoms in the pure structure that allows us to make porous carbons doped with nitrogen or the other heteroatoms. And finally, the wide electrochemical window of peers that allows them to be used in quite some electrochemical devices with large potential window up to 4 or 5 volt. This increase quite a lot of the power. Today's lecture will focus on nanostructured polyionic liquids. The reason why we are very fascinated by the nanostructures simply because that it focus on the interplay of the interface of the confinement and also the electrostatic forces at the nanoscopic scale in pairs. Three types of nanostructures are our favorite. So here we touch colloidal nanoparticles and nanoporous membranes and also the nanocomposite. And in the next 40 minutes, I would probably focus only on the first two, leave the nanocomposite perhaps in the future. So we will first introduce you our work on the colloidal particles and then followed by the porous membranes. As I said, it is a kind of storyline for almost a decade. The story started from quite a long time ago, that is 2011, when we first developed a method to produce pure colloidal nanoparticles by a simple dispersion polymerization. Here we use a vinyl imidazolium bromide monomer with a long acute chain with sufficient length. Here, the length is C12 to C18. It's very interesting because when the acute chain is long enough to polymerize this monomer in water, you need only a water-soluble initiator. Here we use Va86 at 70 degrees C. This immediately produce a dispersion where you can see the image here at the concentration of 5%, right? When you use transmission electron microscope to analyze its morphology, you could see these tiny particles in the size of 20 to 40 nanometers, right? Very simple. You do not need even a stabilizer for the dispersion polymerization because the ionic liquid itself is a kind of surfactant, right? Very simple, clean process. What is really interesting here is the ionic liquid monomer is soluble in water, but the polymer is insoluble. And this creates a very unique situation where you could process the polymers in aqueous media, which is green. And once you process them into the final dry materials, they are water resistant and can be stable against water, right? This is very good for some outdoor applications, for example, coatings. Although the pure nanoparticle synthesis is extremely simple, the inner structure is quite complex. Here are the images that we obtained from the cryogenic electron microscope characterization from C12, C14, C16 to C18. Here you could see a nature morphology evolution from the eccentric multilaminar nanoparticles stepwise to a unilaminar vesicles. When the acute chain is short, in the case of C12 and C14, you could see this multilaminar confined within the nanoparticles, right? Sometimes you call them onion structures. What is very much different from the conventional onion structure is the particle size is rather small, right? 40 nanometers or even less than 40, and you have multi-layer structure in fine, very fine structures. And when the acute chain lengths go further, you ended up with unilaminar vesicular structures. And what is very unique, you can see the facets like morphology, right? It is not spheric as you might expect. The laminar morphology is expected because the hydrophilic backbone, the imidazolium bromide, does not like the long acute chain. So the long acute chain naturally pack them together to form the laminar morphology. What is quite surprising is actually this morphology with defined facets in the case of C18. The reason for that is that the C18 acute chain at room temperature, they are crystalline. So the crystalline process naturally gives the structure anisotropic, let's say, morphology. Now, that is one of the reasons we have this very unique structure different from the previous one. Sometimes we use a name called watermelon to name this type of structure, from onions to watermelon. The centric multilaminar nanoparticle and also the unilaminar vesicle structures are not all I want to cover today. The structure evolves further. What we did next is we use a different ionic liquid monomer here. What we do is we simply replace one carbon in the imidazolium cation by another nitrogen. This is so-called triazolium cation. This simple change of one atom in the entire, let's say, monomer could drastically move the morphology from the spheric nanoparticle to elliptic ones. And with the cryogenic electron microscope, we see these perfect aligned lamina structures. Right? Size here is very small, below, so length is 75 nanometers, diameter is roughly 20 to 30 nanometer, rather small. The feature size is something around 3 to 5 nanometers. We are very lucky to have a very good electron microscope to see the structure. It's this unique non-spheric structure is a balance of the surface energy here between the hydrophilic and hydrophobic domain. So the aqua chain is hydrophobic, and the triazolium cation is hydrophilic. What is slightly different here is the triazolium cation is more hydrophilic than the imidazolium. That modify the surface morphology to allow the formation of the elliptic structure. And it looks very similar to the WASP, let's say, body structure here. Then later we did this tomography reconstruction. It turns out that these lamina structures are not as simple as you might see here, because you also have the so-called perforation of the aqua chain that penetrate through the backbone domains. Right? That is become even more complex, that I will skip that part. Now we have already the multi-centric nanoparticles, unilamina structures. We have the elliptic nanoparticles. The next, we further work with the system is the vesicular structures. Here, different is the wall has multi-lamina structure as well. So that means it's a kind of vesicular structure with multi-layered wall around the central void. And the number of the layers in the wall can be tuned by the polymerization conditions. Right. So this is the next morphology that I introduced into the pure nanoparticle family. And that is actually nanovesicles with multi-layered walls. This nanovesicle structure we observe in both systems, in the imidazolium one and also in the triazolium one. The nanovesicle creates a very unique chemical environment where you could put catalyst inside to run chemical reactions with very high selectivity and also kinetics because of confinement. Right. So here, this nanovesicular structure is unique in the way that it is a good balance between the surface energy, between the bending energy of the lamina, and also the microphase separation, all come together. When it comes to the application of these nanoparticles, here I demonstrated one case where you can use these nanostructures to template carbon materials. So carbon materials nowadays are extremely popular because they are very much used in energy devices, various electrochemical energy devices. And we use the nanovesicle of pure to template the formation of carbon nanocapsules. The fabrication process is straightforward. The only thing you need to do is to introduce the metal ions. Here we introduce iron chloride into the nanovesicular structure. Then after that, straightforward carbonization generate the carbon nanocapsules. The iron in the system during the carbonization react with the nitrogen species there, so it forms iron nitride. And the iron nitride is extremely useful to catalyze the lithium sulfate during the lithium sulfur battery operation. Here we use that as electrode for the as a catalytic sulfur host, and that can achieve both high stability and high performance, and very good performance in the cycler stability. Right. So this is a very unique example where we started with beautiful nanostructures or pures and end up with carbon materials for energy applications. And that is a part I simply give you a research line. We started from 2011 until 2 years ago. We ended up with carbon structures templated by pure nanoparticles. From this slide on, we move on to the next topic, that is nanoporous pure membranes. right? So it's a structure that we developed also a decade ago. This is the starting point of this project. Typically, the nanoporous polyelectrolyte membranes are produced by the so-called layer-by-layer deposition, where you use silica nanoparticles as a template. And then after you conduct the layer-by-layer assembly, you etch away the silicon nanoparticle to generate the nanopores inside. This method is very useful, give you uniform pore size. The disadvantage is that after a heavy working day, you might end up with milligram scale of membranes, right? To overcome this kind of challenge in nanoporous polyelectrolyte membrane, we introduced the nanoporous pure membrane fabrication approach. What we did is rather simple. Here we use a cationic PIL, has the so-called cyanomethyl substituent, and a TFSI as counteranion. So the TFSI is a fluorinated, larger-sized anion, and because of the TFSI, the cationic PIL, although it's ionic, it does not like water, so it's hydrophobic. Then we mix the PIL with PAA together in DMF. DMF is tricky here because PAA in DMF is protonated, and it is neutral. Because it's neutral, now the PIL and the PA can be molecularly mixed with each other, right? If you do that in water, you know that PA is a weak polyanion, so that will complex. You will not have a homogeneous mixture of both. Right? In DMF, we have now a molecularly mixed system. We drop the solution onto a glass plate and dry them at 80 degrees C for 1 hour. It ended up with a sticky film on the glass plate. Then we drop the glass plate into aqueous ammonia solution. You just need to wait for 2 hours. You will end up with a porous membrane. From the scanning electron microscope, you will see the beautifully packed nanopores in the size of 30 to 100 nanometers. Right? So if you go back to the synthetic procedure, you find this is extremely simple. Right? Even a bachelor student without much lab experience, you can train the student in the morning, and in the afternoon, you could achieve square meter scale sized nanoporous polyelectrolyte membrane via the Peel's approach. It's a very simple fabrication process, but it does not mean that the formation mechanism behind is simple. The reality is it took us almost 8 years to fully understand the membrane formation mechanism. So I number them as version 1 and version 2. What we have understand at the beginning is the nanoporous pure membrane is generated by 2 processes in parallel. One is called phase separation. The other is called ionic cross-linking by interpoly electrolyte complexation. The phase separation is expected because the cationic PIL with TFSI and ion is hydrophobic. So when water molecule diffuse inside, the PIL try to avoid its contact with water. This causes a phase separation. Phase separation is a driving force to form the pores. The next process is initiated by the diffusion of ammonia into the polymer blend film. Ammonia reacts with polyacrylic acid. It generates polyammonium acrylate. Now it is actually a polyanion. So you have polycation, you have polyanion. They are already mixed together. This causes immediately the interpoly electrolyte complexation between both, forming the ionic bonding between the imidazolium cation and the carboxylate. In the same time, you release the ammonium TFSI as a low molecular weight salt into the solution. So here, this cross-linking process does not proceed to 100%. Not all the cation, the imidazolium cation join the ionic cross-linking process. We define the cross-linking degree as the portion of the imidazolium cation binding with the carboxylate divided by the entire number of the cations here. So this is we classify them as the cross-linking degree. We will use them later when we study the cross-section structure of the membranes. We think we understand the membrane formation very well, right? We have two processes. One is the phase separation, create pores. One is cross-linking, fix the pores in nanoscopic scale, right? We think we understand very well. Until the point we find a very unique behavior of the membrane to actuate in the acetone vapor. What we observed here is when you cut the membrane into stripe and you put them into acetone vapor. Here we stain the acetone with methylene blue, so you can see that very well. In the acetone vapor, the membrane actuates very, very fast. It looks like your finger touching a fire, so you retract it immediately without any delay, right? This actuation is super fast. In fact, by the time we published 10 years ago, it was the fastest one as a soft actuator at that time. This is quite puzzling for us. The reason for that is the membrane formation mechanism we have proposed in the previous slide cannot explain this behavior. It seems we have not understand the formation mechanism completely. So we do a little bit further analysis here. When the glass plate is placed into the aqueous ammonia solution, you have a diffusion of ammonia and water into the film, right? And diffusion is a kinetic process, means it will go from the top to the bottom. Now the story comes, ammonia is a cross-linking agent, right? So where ammonia is, where you will introduce the ionic cross-links. When the ammonia diffuses from the top to the bottom, you will have gradient concentration of ammonia along the cross-section, right? On the top area, you have full contact with ammonia, and at the bottom, you have less ammonia there. This temporary gradient in the membrane cross-section creates a cross-linking gradient. That means the top part is highly cross-linked, and the bottom part is less cross-linked. How we can prove that? Luckily, we can use the elemental analysis, the elemental mapping across the membrane cross-section. We find an increasing concentration of the sulfur content from low to high, from top to bottom region. This, since sulfur exists only in the TFSI, this can be translated to the cross-linking density that the top part has high cross-linking density and gradually decrease to the bottom part. Now you have porous structure and you have the cross-linking density where top part highly cross-linked, bottom part less cross-linked. In contact with acetone, since acetone will swell the membrane, the bottom part capture more acetone and the volume expansion would bend the membrane with the top surface inward. That explains the bending behavior. Since the membrane is porous and diffusion rate is reversely proportional to the diffusion depth. And this brings the conclusion that the porous structure accelerates the diffusion by 1,000 times. That means the actuation speed is accelerated. It also tells us the sensitivity is very much improved. This high sensitivity towards organic component in bending behavior can be immediately used as a kind of sensor to sense the environment. We demonstrated this by an aqueous acetone solution, where we have an acetone solution concentration from 0.25 mole percent to 1.3 molar percent, a very low concentration. And we could see the stepwise changing of the bending degree of the membrane stripe. So eventually the bending degree and the acetone concentration in water, they can be correlated very nicely in a linear relationship. With that, you could easily tell the concentration of acetone by watching the bending degree of the membrane. They are very sensitive. The gradient structure gives high sensitivity for sensing purpose. The gradient structure is also very helpful to template other functional porous membranes. We use a chemistry here, since we have the PRL with polyacid. If you play the chemistry very well, you could use a gradient membrane to template functional membranes of MOF and COF. In the case of COF, you use trimesic acid to replace polyacrylic acid. Then you could template the morph membrane. Here we use the Hong Kong UST as an example, where you could have gradient size distribution of the morph from the top to the bottom, right? Also the gradient structure existing here. If you, in the case of the KOF, you could have gradient distribution of the KOF crystals from the top to the bottom. So it's a nice example. You can translate the porous gradient structure from the original pure membrane to the hybrid membrane of morph and KOF. They can serve as a porous substrate for specific applications, for example, separation and also filtration purpose. Here, I will not go too much to the details of the morph and KOF membrane. So here, we seems to be more inside the membrane formation mechanism and also the fine structure. We think we have understand them very well. The reality is quite beyond our expectation. The reason for that is for interpolyelectrolyte complex, we understand that if you put them into an aqueous solution of high concentration of a salt, such as sodium chloride, usually the complex will be dissolved, right? Since the ions will come in and dissociate the ionic bonds. This is, however, not observed in our system. When we put our porous membrane in an aqueous solution of sodium chloride at 6 millimole, very high concentration, nothing happens. The porous membrane still exists in the system, not soluble at all. This was quite surprising, right? Apparently, we have not understood the porous membrane in full. Later, what we discovered is a hidden chemistry behind. We call them CMN chemistry, called cation methylene nitride chemistry here. The PIL we used for the membrane fabrication has a cyanomethyl bridge. So the nitride is connected to the imidazolium cation through a methylene bridge. And this unique sequence defines a specific chemical behavior. We know that nitride group can undergo cyclization or trimerization into triazine ring. This is a common chemistry, but this chemistry usually takes place at high temperature, for example, 100 degrees C, in the presence of strong acid or base. The chemical environment we provided for the porous membrane is ambient temperature, and we have only ammonia as a moderate base here. Right? Usually, this would not actually introduce the cyclization reaction. What we find is the nitride group is activated through a methylene bridge when it is sitting around a cation. So here, either imidazolium cation, or it's a pyridinium cation, or even the triazolium cation, we find that the nitride group can undergo the trimerization reaction at ambient temperature catalyzed by ammonia. This is a very unusual chemistry here. The consequence for that is now, besides the ionic bonds connect the porous membrane, we also have the covalent bonding, covalent cross-links to hold them together. This explains why these porous membrane are rather stable in aqueous solution of high concentration of salt. Right? We prove the presence of the triazine by the solid state NMR. Now we see we have a nanoporous PIL membrane. We have gradient structure. We have covalent crosslinks to hold them together. And later, another chemistry we discovered in this porous membrane is actually is related to the triazine. When we apply the triazine for the membrane fabrication, we introduce a new set of chemistry that is a carbene chemistry here. Since triazine cation is a precursor of carbene, when you use the polytriazine for the membrane fabrication in aqueous ammonia solution, the chemistry occurs here is the ammonia diprotonate, the proton here, at the C5 position, and form a carbene intermediate. And this intermediate react further with amine molecule to form a neutral species, carbene amine adduct. And this is a sensitive compound because in contact with weak acid, it can recover the ionic state. So By using base and weak acid, you can shuttle the polytriazine between an ionic state and a neutral state. So if you use a polytriazine for the porous PO membrane fabrication, you create first a gradient, that is the cross-linking gradient we have discussed already. The second gradient is actually a charge density gradient, since the carbene amine is a neutral state. Now we have two gradient structures along the membrane cross-section, right? It looks quite complex, but the fabrication procedure is rather simple. Due to this two gradient structure, you could actuate the membrane by different ways. You can use solvent, you can use also the chemical stimuli to bend the membrane. So eventually the membrane bend to which side depends how strong each bending driving force is, right? And this make the porous membrane extremely sensitive in a chemical environment, can serve as a chemical sensor. The carbene we introduced into the PIL membrane, it is not only useful to design new actuators, but it does has a practical value. Here we use actually the porous membrane as a carbene trap to recycle the expensive metals, here the noble metals, here the gold and the platinum. The reason for that is carbene has a very high selectivity to bind metals, particularly to gold and platinum. And those metals are used in many electronic devices. Right? Everybody has a mobile phone, and most of you have either a computer or a laptop. So you can imagine worldwide how many mobile phones and laptops we have. And these electronic devices, they are let's say used and discarded every few years. Right. So a lot of metals inside. For example, mobile phone has more than 40 elements inside. When you use a mobile phone and you throw it away, actually a lot of noble metals can be recovered. For example, in the processor, you have the metal scraps, and inside you have more than 20 types of different metals inside. And the metal of our interest is gold and platinum because of their high price. So what we demonstrated here is we dissolve those metal scraps in a solution to form the called e-waste water. And you can imagine now you have a mixed metal ions inside. Then we dip our porous PIL membrane inside. Now the carbene chemistry works there to extract gold and platinum from the waste water. So the capacity we reach here for gold is roughly 2 grams of gold captured by 1 gram of the porous membrane. It's very efficient. Some of you may ask, how can you separate gold from platinum? Right. Well, this is really basic chemistry. We know that you can oxidatively dissolve gold. Right. With that, you can separate gold from the platinum and recover gold completely. This addresses a very important environment issue, since electronic waste nowadays are almost everywhere as well, right? And you have a lot of them to be handled. Recover the expensive metal is one of the tasks of to handle the e-waste. In the last 5 minutes, I try to convince you another application of the porous PIL membrane that can be used as the precursor to template porous carbon membrane. Polymers are very common used as precursors for carbon structures because the polymer can be processed into a defined morphology, and then you can carbonize the porous membrane into the carbon with more or less similar morphology. Right? This is exactly the case when we carbonize the nanoporous PO membrane into the nanoporous carbon membrane. The good thing is the chemicals we have, the chemical elements, for example, nitrogen we have here, also naturally ended up with the carbon membrane. So we ended up with nitrogen-doped carbon membrane. We know that nitrogen-doped carbon are very popular nowadays, used as electrode in various electrochemical devices, and it is the same story here. The porous carbon membrane has very beautiful porous structures, and these are the micropores, usually the size above 50 nanometers. And we also have the mesopores and also the micropores. The surface area is decent, 900 square meter per gram. So combining all this together, nitrogen doping, hierarchical pores, high surface area, it makes the porous carbon membrane templated by the PL membrane very popular as electrode for electrochemical devices. Here I demonstrated with one example where we use the PRL chemistry to introduce not only nitrogen but also the selenium as a counter anion into the porous polymer membrane. And after the carbonization, you ended up with nitrogen and selenium co-doped porous carbon membrane. Selenium is very special here because selenium has a boiling point of 800 degrees C. So during the carbonization, whatever selenium you left in the carbon membrane, they exist as a single atom. We verify this by the X-ray absorption spectroscopy in the synchrotron facilities. Right. So we do have a very unique porous carbon membrane doped with nitrogen and selenium. You may ask, what is that used for, right? Well, these heteroatoms make the porous carbon extremely useful as catalyst. For example, here we apply them as in the direct hydrogen fuel cell, where it catalyzes the oxidation of hydrogen into nitrogen and water. If you test it in the device, you see the long-term stability. Here we tested 6 hours and see the high power output of the device, even better than the classic platinum loaded carbon catalyst, right? So outperform the state-of-the-art catalytic system. And the oxidation of hydrogen under the electrochemical environment, we further prove the mechanism. What is the atomic mechanism, how hydrogen is oxidized by the selenium-doped carbon, where we observed that the catalyst of the selenium-doped carbon is activated by adsorption of the hydroxy group in the solution. And this activated the selenium to open the other orbital to accept the hydrogen. Once the hydrogen is adsorbed here, under multi-step of electron transfer, proton transfer, it ended up with di-nitrogen species that eventually leaves as a nitrogen gas. And this recover the active site to undergo the reaction. We are very lucky to have the synchrotron facilities in Sweden in called MAX for the 4th generation synchrotron radiation facility. And also I highly recommend if you have similar need, that is a very good facility to understand reactions at atomic level. With that, I think my time for this presentation is come to the end. I would like to share you 2 messages. That is, polyionic liquids are very powerful materials platform for energy and environment applications. And the next is nanostructured polyionic liquids combines the simple synthesis, the structure beauty, and the diverse functionality. It's great fun to work with nanostructured polyionic liquids. And these achievements, particularly this is a long-term research project, it's also luckily supported by various funding agencies. Those results are not possible if I do not have multi-generation of PhD students, postdoc, also collaborators, and this is the current group photo. And as I said, this project is a decade-long project funded by various funding agencies, very generous, thank for their financial support. And in the end, I would also like to thank you very much for your time to listening to my talk in the early evening. And last sentence, peers in Europe is equal to beer. Right? So if you come to Europe, I hope you enjoy peers. With that, I would like to say thank you very much for your listening, and also thank you very much for the organization to make this online event possible. And yeah, I'm happy now to answer any of your questions. Thank you.